previous lecture, we have talked about bisection method. Bisection method solves algebraic equation of one unknown. In this lecture, we'll talk about another method that does the same job, which is Newton-Raphson method. As you remember that in bisection method, we identify an interval around the root and then iteratively close the interval. Here, of course, the approach is quite different. What we do is we linearize the function fx for which we are trying to find out the root, and linearization of a function essentially means that we take a tangent instead of the function itself. Now, where the tangent cuts the x-axis, we assume that is the root, but as it is not, from there again we draw another tangent. That means another linearization. So essentially this technique is of repetitive linear approximation of the function, because we know that if the function is linear, then finding its root is very easy. We can find the root of a linear function analytically, as we have discussed before. So a nonlinear function, we are linearizing again and again and updating the root iteratively in Newton-Raphson method. So let us see how does the method go. So in Newton-Raphson method, we are again taking this function fx equals 0. So here I have this x-axis and y-axis here, which shows us the fx. This blue line indicates the function y equals fx, and here we have the root which we intend to find out. Now, unlike bisection method, here we start with an initial guess. So x equals to x0 and this 0 within first bracket superscript, which is the iteration counter. This is our 0th iteration. 0th iteration means initial guess. So here we have our initial guess x0, and this vertical line here of course shows the value of y. We want this y to be 0, but definitely y is not 0 here. So we want to reduce this y, we want to come close to it. That is the whole idea of Newton-Raphson method. But anyway, this is our initial guess x0. This is not the root yet. Now, the way we will approach is that we will draw a tangent at x equals x0. That means over here we will draw a tangent at this x0, f of x0, that point. So this is our tangent. The tangent cuts the x-axis over here, that is at x equal to x1. So this is our first iteration. This is our first update. I started from here, x0. Actual root is here. I do not know the actual root. All I did is that I have drawn a tangent here where the tangent cuts. That is my updated root. Now, how do I know this x1? Assuming that I know this x0. The distance between x0 and x1 is h. So this is our h. And we have to figure out what would be this h. Now, looking at this triangle, I know this dotted vertical line is f of x0, and if I take this angle as theta, then h, and here I have x0, so fx0 divided by h will be tan of theta, this angle. However, we know that tan theta is the slope of this tangent. That means this will be f prime, that is dy dx, that is my f prime at x equal to x naught. At this point, whatever the tangent is, its slope, this theta, this tan theta will be f prime x naught. This is from elementary calculus. If you do not remember it, please go through a mathematics book and check this elementary calculus. Now it gives us that h is equal to f of x naught divided by f prime of x naught. So this gives us the step, that is h. Now h is x naught minus x1. Therefore x1 is x naught minus h, and h we have already seen. So x1 is x naught minus f of x naught divided by f prime of x naught. So to find this updated guess of x1, we need only some values at x naught, that is the x naught itself, the value of the function of x at x naught, and the derivative of the function at x equals x naught. Now from x naught, I can again take a tangent. It will cut at x2. You can see that here is my f of x1. Here again this tangent is cutting at x2. So from x1, my next updated guess will be x2. That is my second iteration. You also notice that from f x naught to f x1 to f x2, all these f values are coming down gradually. So from x0 to x1 to x2, we are closing toward the root, and it is very clear that f of x0 to f of x1 to f of x2, it is coming down and it is going toward 0. And every time we are taking this step and we are closing toward the root. Therefore, we can generalize this relation x1 equals x0 minus f of x0 divided by f prime of x0. We generalize this. At k plus 1th iteration, the value of x is equal to at kth iteration value of x minus f of x divided by f prime of x for kth iteration. And this relation we can use repetitively until we hit the convergence criteria, and the convergence criteria should be the absolute value of f of x is less than some predetermined value, that is user defined value epsilon, which will be a small real number. Now, of course, the geometric interpretation is not always necessary to understand Newton-Raphson method. In fact, a more rigorous approach is from Taylor series analysis. So let us say that I have an equation fx and I want to analyze it using Taylor series to get the Newton-Raphson. So how do I do it? So let's say that after kth iteration, somehow I got this solution xk, which is obviously not the right solution or not the acceptable solution to me yet. Therefore, I want to go to next iteration x, that is k plus 1th iteration, and that would be this xk plus some correction, that is delta x. This is the correction. This correction is needed because xk is not the correct solution. Since xk is not the correct solution, if x of xk is not equal to 0, and we hope that in next iteration we will probably get the correct solution, Therefore, f of x at xk plus 1 is equal to 0. Now, we expand this f of x at xk plus 1 using Taylor series. So, xk plus 1 is xk plus delta x. So, if we expand this in Taylor series, which is 0, because I have assumed that I'm hoping that it will be 0, but the Taylor series expansion of this is f of x at xk plus delta x, f prime at xk plus delta x square by 2, f double prime, delta x square by 3 factorial, f triple prime, etc., etc. We are not writing all these terms, rather we are writing this O sign. O sign is something we call order. It only tells us that the order of this remaining term will be delta x square, or in other sense, that if I reduce delta x, the remaining terms will reduce as a square of my reduction in delta x. So within the remaining term, this double derivative with delta x square by 2 will be the dominating term, because delta x itself is small, the higher orders will be smaller and smaller. So the remaining term will be dominated by this delta x square by 2 f double prime. So this is the order of the remaining term. Now we neglect the higher order terms, that means this delta x square as well as the higher exponents of delta x. We neglect them, and neglecting this term is actually equivalent to the linear approximation. If f is a linear function, then you understand that with delta x square by 2 there is f double prime, which will be 0 for linear f, and f triple prime will be 0, etc., etc. So if f is linear, then f double prime, f triple prime, everything will be 0. So when I am neglecting this higher order term and I am taking only this as f plus delta x f prime, essentially my assumption is that this function f is linear. So this is my linear approximation, which we have discussed previously. Higher order term neglecting is same as saying that this is a linear approximation. Now that we have the linear approximation, we are ready to figure out delta x, and we can see that delta x is minus f of x divided by f prime of x at x equals xk. And this gives us this relation. This kind of relations are also called recurrence relations. So we sort of iteratively update this x. So these are recurrence relation, and this relation is at the heart of Newton-Raphson method. This is the most important part of Newton-Raphson method. So now you see, this is a pseudocode, or we also call this is an algorithm for Newton-Raphson method. We don't know the pseudocode or algorithm yet, and it will be discussed next week. But as I mentioned before, that a pseudocode is basically a computer program that is written in our own language. Here you see that the input for a Newton-Raphson method is f of x, f prime of x. These are basically algebraic expressions. X naught, that is the initial guess, and a maximum error value, that is a positive real number where we'll stop the iteration. The result will be x naught, where this f of x naught, absolute value of that, will be less than the maximum error. So we start with y1 equals f of x naught, and then as long as y1 is greater than or equal to maximum error, we continue doing this operation. Our operation is y2 is f prime of x naught, and delta x is equal to minus of y1 by y2, that is minus of fx by f prime x. Y1 is fx and y2 is f prime x, and of course x0 is x0 plus delta x. So we keep on updating the guess and it continues. You can see that the pseudocode is actually much shorter than the bisection method. It's a very slick method, very beautiful method, and its extension application is in everywhere from calculus to optimization. So Newton-Raphson method is a fundamental method that we heavily use in engineering problem solving. So let us see how we use Newton-Raphson method to find the value of root 2. Root 2 is some sort of a mystic number. It has been investigated heavily for last few thousand years, starting from the time of ancient Mesopotamia to Greek, India, everywhere. Early mathematicians explored the value of root 2. So how do you find a good approximation of root 2 using Newton-Raphson method? Let us say that root 2, you know, a irrational number, and it is 1.414, and after that many more digits will come. However, we have to truncate it at some point, and let us see how we can get an approximation of root 2. Our goal is to solve fx equals x square minus 2 equals 0, this equation. Our f prime x is twice x. Now we know the algorithm of Newton-Raphson gives us that k plus 1th iteration x is equal to kth iteration x minus fx divided by f prime x evaluated at kth iteration, which tells us that xk minus fx is x square minus 2, f prime x is 2x. So xk minus x square minus 2 divided by twice x evaluated at x equal to xk, which again gives us k plus 1th iteration x is equal to kth iteration x minus here x square by 2x, so that gives us x by 2, and 2 by 2x, that gives us 1 by x. Both x's are taken as kth iteration value. So this is xk minus xk by 2 minus 1 by xk. So if I remove this bracket, it turns out to be xk minus xk by 2. So that would be xk by 2, and this minus becomes a plus. So that is 1 by xk. So xk plus 1 is equal to xk by 2 plus 1 by xk. This is something, a fundamental equation for finding the value of root 2, and this equation were known since ancient time, although the ancient mathematician knew it only heuristically. Calculus or Newton-Raphson method was not invented in ancient time. So now we can see that how we can calculate the value of root 2 using this, what we call is a recurrence relation. So recurrence relation, because this relation is calculated again and again and again, so these are called recurrence relation. Let us say our initial guess is 2. We don't know what to take as initial guess. Let's say we are trying to get the value of root 2, so we have taken an initial guess of 2. Then I'll use this relation, my x of 1, initial guess is my 0th iteration. So my first iteration value will be xk by 2 plus 1 by xk. So 2 by 2 plus 1 by 2, that is 1 by 5. My second iteration is 1 by 5, that is once again xk by 2, 1 by xk. So x2 will be x1 by 2 plus 1 by x1. x1 is 1.5. So 1.5 by 2 plus 1 by 1.5, which gives us 1.4167. You can see that immediately after second iteration we are closing toward the root. Third iteration is 1.4167 by 2 plus 1 by 1.4167, using once again this same prescription of xk plus 1 equals xk by 2 plus 1 by xk, and we come here 1.414215, which is very close to the number that we remember. So you can see that only in few iteration we are reaching toward the actual root. Usually Newton-Raphson method, it converges in small number of iteration as compared to bisection method. We call this a quadratic convergence, so it converges very rapidly. However, unlike bisection method, convergence here is not guaranteed. Initial guess is important. If we can take initial guess close to the root, it will converge. However, it may not converge. That is one of the problem of Newton-Raphson method. That is why sometimes we use bisection method first to generate a good guess, and then we start Newton-Raphson, which will give us a quicker convergence. One thing you can quickly see here, that Newton-Raphson method uses this idea of xk plus 1 equals xk minus fx by a prime x. So if somewhere we hit a prime x equals 0, then my solution is going to diverge, because a prime x 0 will make this fx by a prime x to be infinity. And even in some cases where a prime x is not 0, it may possible that my solution will not reach convergence. For example, let us say if I have a function like this is my x and this is fx, then it may happen that if I draw a tangent here, it reaches here, it gives me my first root, and then I draw a tangent here, it gives me my second root, and the Newton-Raphson roots oscillates between these two. This problem can be avoided when this root is taken close to the actual root, then we will actually hit the actual root. So Newton-Raphson method has a problem of convergence. It does not always converge. So if we can take care of the initial guess properly, then Newton-Raphson method is very fast and it takes only very few iterations to solve problems using Newton-Raphson method. Now that we have gone little far in using numerical methods, we have seen bisection methods as well as Newton-Raphson method. This is the point where we can talk something about the errors in numerical calculation. We already know that numerical calculations always it will have errors, but now we have idea what kind of errors we are talking about, why always will there be errors. The errors in Newton-Raphson method as well as in most numerical methods come from two sources. First source is a round of errors and second source is truncation errors. So round of errors come due to finite precision representation of real numbers. We know that real numbers most of the time, for example this root 2, it goes from 1.414, but it doesn't stop there. It has many, in fact, infinitely many digits. However, for calculation, we cannot use infinitely many numbers. After some numbers we have to truncate it. So as we cut it down, we basically round off this root 2. That means we are missing out something, and that brings an error in our calculation. Of course, this does not appear in integer calculation or rational number calculation. However, most of the time, we do not have the luxury of using integer or rational number calculation. Numerical calculation mostly involve real numbers, and we have to cut real numbers after certain digits. So this is a round of error. Similarly, we are having truncation errors because many cases in numerical simulation you will see that we are cutting a series. For example, here we are cutting the Taylor series in Newton-Raphson method, and higher order terms we are neglecting. Because of such cutting of series, which is very common in various numerical methods, we will get an error which we call truncation error. These two are the major sources of error. Please understand that when we talk about these errors, we are not talking about human errors, that I made a mistake in programming or I made a mistake in calculation. We are not talking about that kind of errors. Even if I write the best computer program, even if I write calculations absolutely nicely, there will still be errors, and those errors are coming from rounding offs, which is a practical problem because in a computer we cannot represent infinite precision numbers. Similarly, truncation error, that is truncating the Taylor series, this is at the heart of Newton-Raphson as well as in many other algorithms. Therefore, we cannot avoid that, and this will bring errors. In numerical methods, we hope that these errors which are coming from rounding off or truncation, that will not increase as we proceed with iterations. In fact, this should actually decrease. So in worst case scenario, it will remain same and it will not increase. If it increases, then we are in a very bad situation. The property of a numerical simulator that the errors will not increase is the very important property for a simulator, and we call this stability. For an algorithm should be useful, it must be stable. If the algorithm is unstable, then the solver will keep on increasing the errors, and eventually, in fact very quickly, you will see that errors will become unbounded, extremely large, and your solution will be completely unacceptable. That will have no practical value. So all numerical simulators must be stable. This is a very important property, and we'll discuss this more as the course progresses. Finally, as you remember, we have talked it again and again, and you should keep in mind very clearly that numerical simulations cannot be error-free. There will be always errors. Our goal is to reduce the error to a level where we think that the solution is acceptable. The accuracy of acceptable solution, that depends on the problem you are solving, the application that is in your mind. There is no hard and fast rule where a solution will be acceptable, where a solution will not be acceptable. Now to summarize, we have seen Newton-Raphson method solves the algebraic equations of one unknown, fx equals 0 type equation. Bisection method also does the same thing, but here the procedure is different. Here we start from an initial guess of the root. In bisection method, we have started from an interval within which the root will reside. Here in Newton-Raphson method, we linearize fx, and that way we update the root iteratively. In bisection method, we start from an interval and then you close the interval iteratively. As an exercise, you use Newton-Raphson method to evaluate 2 to the power 13, that is cubic root of 2, and you use manual calculations, use a standard handheld calculator, and do not write a computer program. There is no need to write a computer program yet. You follow the same procedure as I have shown here. So you start with this x cube minus 3 equals 0 as fx, and then you use the Newton-Raphson algorithm to calculate iteratively the value of 2 to the power 1/3. That's all for this lecture. Thank you, and I'll see you in next class.